Hello everyone, thank you very much for watching this presentation. The paper presented here is entitled Numerical Analysis of Semi-Displacement Vessels and Headweight and describes a so-called 2D+T method for the computation of high-speed ships in waves. This paper is a collaboration between my co-authors Marleaux and Moustafa Abdel-Maksoud and myself, and was carried out at the Institute of Fluid Dynamics and Ship Theory at Hamburg University of Technology. Let me begin by giving you some reasons why this topic might be of practical interest. First of all, the term semi-displacement vessel refers to vessels roughly operating between fluid numbers of 0.5 and 1. And as the ship speed increases, the importance of hydrodynamics and ship design often increases as well. For example, seakeeping might become more and more of an issue as the excitation forces tend to increase. Dynamic instability may become an issue, especially for fast ships, and also slamming should be considered, especially for catchment vessels. Unfortunately, non-linearities of the flow tend to play a more important role as the ship increases, as the ship speed increases. So the application of well-established linear methods for the computation of the flow is often questionable. Examples are transverse effects, separation, ventilation, and generally large deformations of the free surface. All of those can be observed in the picture shown on the slide, which shows a fast naval ship. While there are a variety of well-working methods available, we think that there's still a lack of enough suitable and efficient nonlinear methods for the computation of higher speed vessels. And therefore, in this paper, we describe such a method and show that generally favorable results may be obtained when computing the motions of fast ships in waves. Before presenting the results, I will give a quick overview first of how the method works. The method is based on 2D+T theory, and in this theory, the 3D flow is actually replaced by several 2D flows in Earth-fixed transverse crossplanes. This is supposed to be illustrated by the picture shown on the slide, where many black rectangles in the right picture represent the crossplanes. As the ship moves through these crossplanes, it causes flow in these crossplanes, and we compute the time development of these flows. And together, the many two-dimensional flows approximate the original three-dimensional flow. This approach makes the method more efficient as if the original 3D flow would be computed. However, for this approach to be valid, the ship should be fast and slender so that the flow is mainly two-dimensional in the crossplanes. We assume potential flow, and we solve it by applying a boundary element method and a mixed Euler-Lagrange procedure. In this procedure, the nodes of the boundary element mesh are treated as fluid particles, and their motion is being tracked. By using this approach, nonlinear boundary conditions can be accounted for quite easily. This next slide shows a video illustrating how the method works. So we see here a fast planing vessel moving into the fluid domain, and as it moves through these cross-sections, it causes flow in these cross-sections, and we compute the time development of these flows, and together the many 2D flows approximate the 3D flow. For completeness, we've listed the most important equations on the next two slides, but I will keep this as short as possible. As mentioned, the flow in the 2D cross planes is treated as fully nonlinear potential flow, which is governed by velocity potential and the Laplace equation. In this method, the total velocity potential is split up into a disturbance potential accounting for ship and a known linear wave potential. We use a collocation boundary element method with linear elements to solve the flow numerically. So there's a system of equations that is closed by using the boundary conditions. On the hull, we use hull boundary conditions stating that there's no flow through the hull, that is phi n, the normal derivative of the velocity potential is known there. A similar boundary condition is used on the outer boundaries, and on the free surface, the velocity potential phi itself is known. Then the time development is computed by assuming an initial solution. In our method, this is just the undisturbed free surface. And then phi is known at the free surface. The system of equations from the BM can be solved, and we get phi and phi n at every node on the boundary as the solution. Then gradients can be computed by fitting a local polynomial. And after that, we can evaluate the boundary conditions at the free surface to step the free surface forward in time. So we use the kinematic boundary condition at every node of the free surface to move the nodes. And then we compute the change of phi at the free surface by using the dynamic boundary condition. Note that the shape of the free surface is computed explicitly, but the value of the velocity potential is determined implicitly. So this is kind of an implicit Euler treatment. This partially implicit treatment is motivated by the solution of the equations of motion, although a fully explicit treatment is also possible. However, since the additional overhead is limited and the partially implicit treatment proved to be a little less sensitive to grid treatments, it is chosen here. What is more important is that a first order treatment was shown to be less suited in some numerical tests, which is why actually a second order variant is used in this paper based on the trapezoidal rule. The formulas are not shown on the slides due to the limited space, but they're in the paper. Note that the upper indices n denote the time level in the formula shown here, and the lower indices n denote the normal derivative. After we've computed the flow, we can evaluate the pressure using Bernoulli's equation, and in this equation, the local time derivative is simply computed by a simple backward finite difference formula, which proved to be accurate enough in our cases, and was also quite robust and easy to use. When solving the equations of motion, added mass forces have to be considered, which brings the equations to the form shown here, and a discretized version is shown on the right. Note that the acceleration also appears on the right-hand side of the equation, so an implicit iterative solution is suggested, but again, an explicit treatment is also possible as long as the estimation of the added mass matrix A is good enough. Treatments of the numerical grid are quite essential to perform the computations presented here. First of all, we use regridding of the free surface, for which the same polynomial fit as for the computations of the gradients is used. And also we use jet and spray cutting. That is, thin jets and spray are removed from time to time from the fluid domain by cutting it off and simply linearly interpolating new nodes between the cut nodes as needed. This makes the solution more efficient and more stable, and even possible in some cases. There's also a separation model, which is used to model non-viscous flow separation from curved hull surface. And in this model, the flow is assumed to separate from the hull if there's negative pressure on the hull, that is, the pressure on the hull part next to the free surface is below atmospheric pressure. Thereby, it is assumed that there is ventilation happening due to the pressure difference between the free surface and the hull surface. It may happen, and then the hull nodes for which this is the case are simply turned into free surface nodes. It may happen that thin jets separate this way, and if that happens, we use the Euler equation directly to determine the change of the velocity at those nodes. And then we can compute phi and phi n directly at these nodes. So there are no unknowns actually at these nodes, which need to be determined from the boundary element method. And this makes the solution more stable and more efficient as well. And it may also happen that reattachment occurs, and this is achieved by simply neglecting entrapped air if there's an intersection between the free surface and the hull surface. This is a rather simple treatment, but it has been used successfully before by others and seems accurate enough to be able to continue the computations even after the occurrence of reattachment. So after giving you a short overview of how the method works, I will be presenting the results. First, a look at the case that has been studied in the paper. We considered a hull belonging to the high-speed displacement hull form series, which was investigated experimentally and numerically by Bloch and Beukelmann in 1984. They conducted sea-keeping tests and also did numerical computations using different strip methods. They actually found quite good agreement despite the high forward speeds between numerical and experimental results. And these good results of the strip methods, in spite of the high forward speeds, this motivated Koenig in 1988 to study the vertical force distribution acting on the hull in more detail. And he used actually a segmented model to conduct these studies. And the cases from these experiments that we considered in our paper are steady forward motion in calm water, forced heave motion in calm water, and free heave and pitch motion in regular head waves. The body plan of the model is shown also on the slide, and the table contains the most important information about the hull. The length of the model was 2 meters. The block coefficient is quite low, below 0.4. And the fruit numbers considered in the paper are 0.57 and 1.14. And it should be noted that all computations are carried out in model scale. I'll be presenting the study results first. We see here on this slide the computed free surface profiles at several sections along the hull. The results for fruit number 0.57 are on the left, and the results for fruit number 1.14 are on the right. In each plot, the forward sections are depicted on the right, and the aft sections are depicted on the left half of the plot. It can be seen here that for fruit number 0.57, they're just moderate deformations of the free surface, just a little flow separation at the bow. This becomes much more violent at fruit number 1.14, where this flow separation extends further aft and the deformations become larger. This slide presents the results for the vertical force distribution for fruit number 1.14. X minus X AP is the distance from the transom stern. So X minus X AP equal to 0 denotes the transom stern on the left of the plot, and on the right of the plot at X minus X AP equal to 2 is the bow. In the left plot, the total force has been split up into a hydrostatic part and a dynamic part. The hydrostatic part contains hydrostatic pressures up to the undisturbed free surface. And the dynamic part is obtained by subtracting the hydrostatic part from the total force. And it can be seen in the left plot that the so defined dynamic force is a considerable part of the total force. And in the right plot, the distribution of the dynamic force is compared to the experimental results obtained by coining using the segmented model. The red lines are the experimental values, and the blue line corresponds to the simulation results obtained using the presented method. And it can be seen that there's good agreement except for the sections close to the transom stern, and these deviations might be explained by the fact that the pressure is atmospheric at the transom stern, which cannot be accounted for by this method, as the flow at a certain cross-section is only influenced by what happens upstream of this cross-section. This is usually the most important 3D effect that has to be kept in mind using this method. And there's also a similar 3D effect at the bow, but this seems to be less of an issue for this model as the shape of the hull is very fine at the bow. On this slide, variation of the temporal and spatial resolution is presented. We use actually a current number-like criterion to determine suitable time-step size at each time step. And this variation shown here shows that there was little variance, little dependence of the results on the chosen time steps. And to keep same setup for all computations, a value of C equal to 0.2 has been chosen as for all computations. The right plot shows a variation of the sinkage, which was also investigated in the experiments, and there's again good agreement in the forward and midship sections, but again the method overpredicts the forces at the transom stern due to the neglection of the 3D effect at the transom stern, where there should be atmospheric pressure actually at the transom stern, which cannot be accounted for by this method. Next, I will be presenting the results from forced motion simulations. These runs, the hull performs forced heave motion at a certain frequency, omega, and a certain amplitude, eta 3a. From the simulation, we then get time histories at Earth-fixed cross planes rather than ship-fixed cross sections. So we obtained the force histories, the histories of the vertical forces at ship-fixed cross sections by linear interpolating from the results of the Earth-fixed cross sections. When we have these time histories at ship-fixed cross sections, we can then expand this into a Fourier series and compute the sectional added mass and damping coefficients from first order Fourier coefficients, as illustrated by this formula on the slide. The restoring coefficient, which also appears, has been defined just as in the experiments in a hydrostatic manner. The slide shows the results for the distribution of the heave added mass coefficient, the sectional heave added mass coefficient. And for the two considered fruit numbers, fruit number 0.57 is on the left column, and fruit number 1.14 is on the right, and a frequency of omega equal to 5 seconds to the minus 1 is in the upper row, and a heave oscillation frequency of 13 seconds to the minus 1 is in the lower row. the amplitude was 0.01 meters. And we see that there's generally good agreement between the numerical and experimental results. For both fruit nums, actually, the agreement improves at higher frequencies, which may be attributed to the fact that the assumption of mainly two-dimensional flow is more appropriate at higher frequencies. Discrepancies are mostly confined to the stern region, where the already mentioned neglected 3D effect plays a more important role. And this slide shows the corresponding results for the sectional damping coefficient, for the distribution of the damping coefficient. There's good agreement as well. Again, only at the transom stern and stern region, the results vary slightly from the experimental results. This slide compares the results of different methods for the case omega equal to 5 seconds to the -1 and the higher fruit number 1.14. The upper plot shows the distribution of the sectional added mass coefficient. Again, the red line shows the experimental results, and the blue line, the dark blue line, shows the simulation results. And the dashed blue lines refer to methods by Sun and Falkenson and Tsao, which are also T+T methods and are therefore quite similar to the method presented here. However, in the method by Falkenson and Tsao, the flow was linearized in a way that the interaction between the steady flow and the unsteady flow was not accounted for. And this interaction is actually more important very often at lower frequencies. That may be the reason why their results deviate more from the experimental results than the results of the fully nonlinear methods do. And the dashed red lines shown in both plots refer to the two strip methods that have been used by Koenig and Beukelmann. And the main difference between these two different strip methods is that the version 2, denoted by V2 in the plot, accounts for forward speed effects in a more accurate way than the version 1 does. And as it can be seen on the plots, it actually agrees better than with the experimental results than version 1 does, especially in the bow area, when we look at the added mass distribution. I will now move on to the case for with free heave and pitch motions, and I will be first showing a video of the simulation showing the hull and the computed free surface in the several cross planes. The case presented here corresponds to fruit number 1.14 and an incoming wavelength lambda by the ship length L equal to 1.5. We see that at the beginning of the simulation, all the cross planes are in front of the hull, and then the hull starts to move forward at the prescribed forward speed into the fluid domain. And as soon as it has passed the first section completely, then the equations of motions are solved, and then also waves are accounted for in the cross sections and in the boundary conditions when solving the flow. And as the video starts, we see that the hull starts to move now as it enters the wavy area, and we see this large amount of spray developing in the bow area whenever the hull hits into a wave crest, and these time instants actually correspond to the time instance where the hull experiences the largest accelerations, as can be seen in the time histories, which are also shown on the plot here on the right half of the slide. And from these time histories, we can compute the motion amplitudes. And the next two slides show the computed motion amplitudes, which we have computed from the time histories. First, the results for the lower fruit number 0.57 are presented. The heave amplitudes are shown on the left, and the pitch amplitudes are shown on the right. And we see that the results agree quite well with the experimental results. Only the heave amplitudes deviate slightly more from the experimental results. However, the nonlinear method performs generally better than the two strip methods, which have been used by Bloch and Beuchelmann. Nevertheless, we think that the results of strip methods are quite useful also in this case, considering the low computational effort which is necessary for strip methods. Again, version 2, which accounts for forward speed effects more accurately than version 1 does, gives better results here for this case. On this slide, the results for fruit number 1.14 are presented, and actually the agreement is a little better than for the lower fruit number. When we look at the results from the presented method, which correspond to the blue lines, to the dark blue lines. Actually, surprisingly, in this case, the strip method version 1 seems to produce better results than version 2 does. And this motivated Koenig's work partially. And what is also shown in these plots are the results obtained by Faltinson and Sau, which was a linear 2D plus T method working in the frequency domain. And while these results also agree well with the experimental results, there are slight differences in the resonance area, where the nonlinear method performs a little better, and this might be an advantage of the nonlinear method. So, which conclusions may be drawn from this investigation? First of all, we've presented a 2D plus T method based on nonlinear potential flow and a BAM, and we showed that numerical grid treatments are necessary to perform such simulations, and we presented grid treatments that can compute the flow in the presence of jets, spray, and separation and reattachment, and it was shown that satisfactory results may be obtained when computing the seakeeping behavior of high-speed ships. And for future work, it might be considered to improve these grid treatments. The correction of three-dimensional effects can also be pursued. The computation of the local time derivative of velocity potential can be improved, and very important is, of course, more validation, the consideration of more degrees of freedom, different sea states, and so on. So let me thank you for watching this presentation, also in the name of my co-authors, Marleaux and Moustafa Abdel-Maksoud from the Institute of Fluid Dynamics and Ship Theory at Hamburg University of Technology. We hope to see you online for the discussion and look forward to your comments, questions, and suggestions for improvements. Thank you very much.